Now we are ready to move on to our next topic of the course, the second half of the course, which is mathematical logic. What is logic for you? Please share some ideas. What do you mean by logic? Whenever a friend tells you something absurd, then don't you say to them, please be logical. What does that mean?
Don't contradict yourself.
Don't contradict yourself. Okay, maybe that person is not contradicting themselves, but contradicting some well-known fact. Any other answers? I mean, what is logic for you?
There is something called a established fact, then we say that it is also.
A well-established fact. And what is the meaning of well-established fact? That is accepted everywhere. Okay, so it's something like the axiom, the concept of axiom that we talked about. So, very loosely speaking, logic is said to be the study of reasoning. Okay, how do we reason? If we want to understand, there is some conclusion, right? So suppose now, right now you are sitting here, and once perhaps your cycle is parked in the open, and there is water on your cycle seat after you go out. What will you conclude? That it rained, correct? So, how does this deduction happen in your mind? The study of that process, the study of what goes on here, that is logic. The science of arguing, the science of reasoning, that is logic. If I say right now that Mr. Narendra Modi is the Prime Minister of India, is this statement true or false? True. What is the meaning of truth? The cardinality of any set is strictly smaller than the cardinality of its power set. Is that statement true or false? True. Why is it true? Yes, loudly. We are able to prove it. Correct. But is the concept of truth and proof exactly the same? Can you prove that Modi is the Prime Minister of India? So right now you are talking about two different things, right? We tend to mix them every time. If we have a proof of something, in the court of law, if evidence is presented, there is a CCTV footage, there is a written note, then that is taken as a proof for something that happened. And therefore, somebody concludes that the claim that is supported by this evidence is true. But we need to understand the difference between truth and proof. So, that's one of the important goals of this course on mathematical logic. You should understand what is the difference between truth and proof. And then the natural question is, if something is true, can we prove it? Not always. Can you give me an example? And please be aware, I mean, in real life, perhaps what you say is correct, but in mathematics, what do we want to expect? We can prove everything that we can. Sorry, what did I ask? Which implication did I ask? If something is true, then can you prove it? Not always. Can you give me an example?
Axioms. The sun rises in the east.
No,
The sun rises in the east. Is that an axiom? No. No, he was talking about axioms. That's why I asked you. So you cannot prove that?
Like it relies on you naming the direction east in the first place.
Okay, but that has some human involvement. Yes, okay. What's your argument?
Like axiom is something we all accept that as a truth.
Axiom is something that we all accept as truth, correct? And therefore there is no proof?
There can be a proof, but
Okay, that raises an important question. What is the meaning of proof? Whenever we say that this is this theorem, what does it mean?
it follows from
It follows from
the axioms we have.
it follows from the axioms, right? If something follows from the axioms, and how does it follow?
Like implications.
Using some implications, but those implications also have to be well defined implications. So there should be some rules which govern our proofs. So you remember there was one particular Latin term that I used while proving that strong induction and weak induction are the same. Modus ponens, right? So if A implies B is true and A is true, then you can conclude that B is true. Now this is called a rule of inference. So you start with axioms and you use rules of inference to conclude, to complete a proof. You conclude something new. Then again you collect a few statements and then from a combination of them you conclude something new. And again from that combination you conclude something new. And if at all, okay, now this is the most important thing. If at all after finitely many steps you could reach a place where you wanted to reach, then you say that there is a proof of that statement. I want to highlight the word finitely many steps. In mathematics, we never write infinite length proofs. Can we? Yeah, I mean that's same as Munchausen's trilemma. We do not accept arguments which trace back to some argument which again trace back to another argument and there is an infinite regression. We don't want to do that because we do not have enough lifetime. So ultimately the concept of a finite length proof, yeah, I mean a proof could be very long. There have been papers which are 100-page long, 200-page long. I have told you that in Principia Mathematica, the proof that 1 plus 1 is equal to 2 is some like around 300 pages long. But 300 still is a finite number. 300 pages is not an infinite length proof. It's still a finite length proof. So the concept, something which we need here is what is the concept of a proof. So start with axioms. And use rules of inference and finite length. Finite length tree of inference of deductions. Okay. So you combine lots of things. Yeah, I am calling it a tree because you start from two places, then you combine them to obtain one thing. Now you combine this thing from with something else, and then you combine them. So you are forming a tree. So these are some essential features of a proof. Okay, what about truth? What is truth? When do you say something is true? Please don't tell me that it is only the statements which have a proof are true. Yeah, that we'll see later. But if you are not studying mathematics, then also you use the words true and false. somebody is a liar, somebody is always a truth teller. Yeah, I mean, truth and false, these concepts are embedded in our mind since childhood, even if we don't know any mathematical logic or philosophical logic. So, how do you decide whether something is true or not? Somebody already answered here in the beginning. So, it depends on our common perception. It depends on human understanding. Are you getting the point? Our understanding, our common consciousness is what determines the truth or validity of a statement. So, this has to do with human consciousness. Or understanding. Well, there is another branch of logic which studies our understanding. We are not going to do that. One simple example that I had already given you in the first lecture is that the meaning of the words and or, they are the same in our minds. Yeah, there is no ambiguity. No matter what our mother tongue is, no matter where on the planet we reside, our understanding of some words is always the same. Yeah, as long as we are not color blind, our understanding of colors is still the same. So that's common human consciousness, common human understanding. And in linguistics, there is a very specific term for that. And that term is called semantics. Semantics is the study of understanding. On the other hand, yeah, I mean, that has to do with humans. Yeah, semantics part has to do with humans, whereas whatever you see here, you start with something called axioms. And what are axioms we don't question. I can give you 2 axioms and then you can work with them. So basically, I don't have to tell you about this. I can also teach a machine that this is something which you start with. These are the rules using which you deduce something in finite length, you obtain the conclusion. So basically, I can program everything on this side. Everything I do is a symbolic manipulation. That is called syntax. Okay, now when I say syntax and semantics and symbolic manipulation, obviously whenever human beings are going to code something, yeah, whenever we code something into a machine, into a program, then we are not stupid. Yeah, we will try to code it in such a way that matches with our understanding. Correct? The rule of inference, modus ponens, is a natural rule. We all understand that. Yeah, if A implies B is true and if A is true, then B is true. We all agree with that. There is no ambiguity. So therefore, then we decide that we add that rule of inference into the proof system. Right? So we are not going to make any stupid choices about these rules of inference. However, the question still remains. Whatever we want to say is true, can we code up enough rules of inference so that every true statement has a proof? Are you understanding the question? That whatever we want to, whatever we know is true, can we formalize the process that goes on in our brain so perfectly that the true statements are precisely the ones whose proof exists? And the answer to that, in some formal systems, yeah, of course, formal systems, we are not talking about everyday life situations, but something which is which lies at the core of our reasoning. So for some formal systems, this result is called Gödel's completeness theorem. So Gödel's completeness theorem says that, I mean, there are two parts of it, completeness and soundness, soundness and completeness theorem. And completeness theorem. The soundness part says that if a statement has a proof, then it is true. This is soundness. Okay, if I can prove something, then I must have proved a true statement. And conversely, if a statement is true, then it has a proof. Now, think about it for a moment and tell me which of these two statements is more plausible than the other. The first one, right? If I can prove something because I am a human and I wasn't stupid enough to code up some wrong rules of inference, obviously if I know that I have a proof, then yes, that is a true statement. However, if I just know that something is true, then I have to come up with a proof of that, a finite length proof. That is a non-trivial thing. And that's why we needed a genius like Gödel to come up with this statement. Yeah, Gödel proved that proof and truth are exactly same in formal systems. Okay, so here now our question becomes, what formal systems are we talking about? Because if you want to code up rules of proof, then at the same time you should also be able to code up the statements whose truth you want to verify. So the statements should also be written in terms of some symbols. Right? So that symbol, those symbols are called logical symbols, right? And those logical symbols are usually, those symbols together, they are called alphabet, and they are divided into two parts, logical symbols and non-logical symbols. Or in some sense, a language and a meta-language. Okay, I am using the word meta here, so let me clarify something. So let us have a look at different branches of science. Can you name a few? Physics, chemistry, biology, mathematics, right? Okay, so you can say that physics is applied maths. Chemistry is applied physics, right? In a very loose sense, yeah. Don't take offense if anybody is fond of these things. Then biology is applied chemistry. However, how do you go in the reverse direction? The operator, in that case, we can call it to be meta. What is applied math, what applied is mathematics? Philosophy, or in our course we'll call it logic. So mathematics is applied logic. But then you can also ask, what applied is mathematical logic? The answer to that question is metalogic. You understand? Metalogic lies at, metalogic is the logic that we use to reason about logic. So we have to distinguish between these two levels. Then what's the next natural question? Metalogic, right? It never ends. Yeah, if you want to argue about metalogic, then you will need the meta version of that. So meta and applied, these are like opposite directions. Any questions so far? Right. So we need to talk about some symbols which are logical symbols and which are non-logical symbols. But these are the two most important things, okay? Whatever logic you study, you always have to ask about syntax and semantics, and at the heart of every logic lies the syntax semantics duality. Syntax semantics duality, this is one example of syntax semantics duality. It says, okay, now this is a very philosophical statement, that an idea can manifest itself in two different forms, but it is the same idea. If you have read some literature of saints, yeah, they would all say this duality. Yeah, two different things, their existence is exactly the, it's related to one idea, because ideas, they are beyond humans and they are beyond machines. Ideas are abstract concepts. The semantics is their manifestation in human consciousness, whereas syntax is their manifestation in machines or in formalism. Yeah, I mean, when I say machine, please don't only think about computers. I mean something that is formal and has rules to work with. Okay, so this syntax semantics duality lies at the heart of every single inquiry we will do about logic, and then ultimately we'll prove that statement. Simultaneously, please keep these questions in your mind while we are studying logic. What is a theorem? Yeah, you have studied several theorems, but what is a theorem? Yeah, I am doing the same thing that I did in the first lecture. Yeah, I am asking you to think about the things that you know, or you believe you know. Yeah, but you don't know. Okay, then I mean, let's say how to teach a machine. Yeah, I mean, how to come up with rules of inference or proof systems. That's a very interesting game. There is an entire branch of logic called proof theory that is entirely devoted to this idea. Nowadays, are you aware that there is a branch of computer science as well as mathematics that's called homotopy type theory that is being used to formalize proofs in mathematics? Formalize as in, if somebody has written a proof on a paper, then they are actually trying to derive the same statement from axioms using rules of inference. Yeah, there are some massive projects like classification of finite simple groups. Now in the past decade, people have formalized that proof. Everything just follows from axioms. Now computer has the entire proof of classification of finite simple groups. By the way, I mean, yeah, you probably don't know what I'm talking about, finite simple groups. You only know finite. Yeah. But simple groups are something like atoms. Yeah, they are groups. You have studied groups. Yeah, I mean, rings you have seen. Groups are sets, non-empty sets, which have a binary associative operation, which has identity and inverse. Okay, that's all. So finite simple groups, the classification of them, entire classification, it took around 3 decades of several mathematicians. Yeah, I mean, maybe over 100 people. Yeah, they all work together towards the same goal. Yeah, and this is a very big achievement of humanity, the classification. The classification is written in a large book called the Atlas, Red Atlas of Finite Simple Groups. It's a massive book. I have seen that. There are very few copies of it. So, but how to teach a machine, how to train a machine? I'm not talking about machine learning here. Okay, machine learning is a very different topic, but here we are trying to understand how to explain basic things to a machine. Another thing is, yes, so there is something that I want you to think about always when you talk about a mathematical structure. Can you give me some mathematical structures that you know of, well-known mathematical structures?
Vector spaces.
Vector spaces. So maybe one particular vector space.
R cube.
Okay, I'm talking about R. So what should I write? What is the structure of a vector space?
Plus like vector addition and scalar multiplication.
So plus is a map from R cross R to R. Then scalar multiplication. So what should I write scalar multiplication as?
Usual multiplication.
Usual multiplication, will that work? If I instead of R I take R2, will the usual multiplication work as, what is the usual multiplication for R2? It doesn't exist. See, we are not trying to say ring, we are trying to say a vector space. So actually you have multiple operations. So you have one operation MR from R to R for each real number R. And then you also have something else. There is one special element in every vector space. Very good. And 0 is an element of R. But an element, I can also write that it is a function from R to the power 0 to R. What is R to the power 0? The set of functions from 0 to R. How many functions are there?
How can there be a function?
0 to R. 1. Just one function. Yeah, 0 is empty set. How many functions are there from empty set to anything else? Just one function. whose graph is empty, with empty graph, right? There is only one function. So now r to the power 0 is a singleton. It consists of only one element, and now one function from singleton to r, that just picks out one element, right? So this is our structure. Okay. Now if you are given two structures of the same type, then how do you define the notion of a homomorphism between them? I mean, what is a homomorphism of vector spaces? It's called a linear transformation, right? Linear map or linear transformation, that's just another name for vector space homomorphisms. So vector space homomorphism will preserve addition, it will preserve scalar multiplication, and it will preserve 0. But do you ever say that the associativity of addition is preserved by the homomorphism? Do you say that commutativity of homomorphism of addition is preserved by homomorphism or a linear map? No. So you understand? See, this is structure. And we can list some properties about the structure, that plus is associative, plus is commutative, plus has identity, plus has inverse. These are all properties. Then scalar multiplication, you will have some more properties, yeah, mr of ms is equal to mrs and other properties, but they are all properties. You understand that the difference between properties and structures? A homomorphism, I mean, if you understand the word, it is a Latin word. Morph stands for structure, and homos is the Latin word for, morph is preserving and homos is structure. So structure preserving map. We don't care about properties, only structure preserving maps. So homomorphism preserves structures but ignores properties. I mean, ignores properties as in it doesn't try to destroy them, but we don't talk about properties when we are defining homomorphisms. Similarly, if I say that partially or two partially ordered sets, what is the structure there? For a partially ordered set, what is the structure? The relation is the structure. It is a binary relation. That is part of the structure. And when we say an order preserving map, a monotone map, then what does it preserve? It preserves the structure, it preserves the order, but we don't care about whether it preserves reflexivity, because we are always talking about the same type of structure on both sides. So always think about this, yeah. Your mathematical thinking will be much clearer once you ask this question: what is part of structure and what is part of properties? Even if I am simply given integers with 0 and addition, this is an abelian group, yeah. Or if I am just given integers with addition, then the one thing I should ask, that does there exist an identity element for this addition? So identity can also be treated as a property of the addition. However, unless it is unique, you cannot really separate it out. Identity, there could be many identities, right? Okay, I am not going to go into the details of algebra, but please make sure whenever you study a new topic in mathematics, always ask what is structure, what are properties. Metric spaces you will study. Probability space, what is the structure and what are properties. When you study topological space, what is structure, what are properties. Every time keep this distinction in mind. Just asking this very simple question will clarify lots and lots of concepts for you. That is also one purpose of logic, to make sure you understand this difference. I am going to do one other simple exercise. So we have been talking about formalism, right? Now I am going to ask this simple question. What is x square plus y square minus 1? Yes, I want all possible answers for this. It's an expression, yes. Then anything else? Loudly. Depends on how we define x inverse.
X and Y.
X and y, okay. Anything else? I mean, does this not remind me of anything? Circle. Right, x square plus y square minus 1. Do you want to elaborate? What circle? It will be a circle with center at origin and radius 1. Right? We suddenly jump to this conclusion. Yeah, that's the first thing. If I were not talking about formalism, then even he wouldn't have got the correct answer that it's just an expression. Whenever somebody sees x square plus y square minus 1, then it's a circle. No matter whether there is equal to 0 in the front, whether there is less equal 0 in the front. Once we see that expression, like it's similar to the question that I asked in the beginning of the course. Give me examples of functions. Sine. Where? What is domain, what is codomain? X square. What is x? That is what happens. So again, we are continuing with our tradition of asking questions about how we think. So I am going to write down 4 different things. This is called a term in logic. Then x square plus y square minus 1 from r square to r, where a pair AB is taken to a square plus b square minus 1. This is a polynomial function. This is a polynomial. Term is a polynomial. In this case, the term is a polynomial. Then this is a polynomial function, or I can say its interpretation of term. Now there is a third thing. This is x square plus y square minus 1 is equal to 0. This is an equation, this is a polynomial equation, or in logical language, this is called a formula. Okay, so term and formula are logical terms. And polynomial equation, these are our usual understandings. Similarly, polynomial function is our usual understanding, but interpretation of a term is our logical understanding. Okay, and finally, the set of all AB in R square such that a square plus b square minus 1 is equal to 0, this is called, in logical terms, this is called a definable set, or in this is solution of a polynomial equation that you call as a circle. So there are 4 different things: polynomial, polynomial equation, polynomial function, and the solution set of a polynomial equation. Don't equate all of them. Yeah, that's also one of the lessons of this part of the course. Right? So let us stop here.